Okay, so we're going to be studying Le Chatelier's principle, which you actually learned last year, but some of you may have had difficulty with it because at the point where you learned it last year, you didn't even understand what equilibrium was. You didn't understand that you have reactants and products, and at some point they're going to go into equilibrium, meaning the rate in the forward direction is the same as the rate in the reverse direction, and that you might not have equal amounts. You probably don't have equal amounts. One will probably dominate. Either you'll have more reactants than products or products than reactants. But once you get to equilibrium, those concentrations stay the same. You didn't really fully understand that last year, but now that you do, Le Chatelier's principle should make a lot more sense. First of all, Le Chatelier's principle is the concept that when you have a system at equilibrium, you are going to put stress on that system, and when you put stress on that system, it will cause the equilibrium to change. Okay, so let's say you have a system at equilibrium, and all of a sudden you come along and you do one of these three stresses. You either add or remove some reactant, you change the pressure, or you change the temperature. When you do that, it's going to mess up something. It's going to mess up something about the reaction, and the reaction won't be at equilibrium anymore. But I hope we all realize that every time a reaction's not at equilibrium, it will try to get back to equilibrium. That is the whole point. And that's what Le Chatelier's principle says. If you put stress on a system, the system will get itself back to equilibrium. Okay, so we're going to talk about three different stresses. The first two I would kind of lump together into being similar with each other, and then the last one has some very important differences to it. So let's go ahead and start with adding or removing a reactant or product. So let's say we have a reaction. It's at equilibrium. We know that equilibrium means that it has a product concentration value ratio per reactant, something like that. So let's say all of a sudden we have a reaction of A is in equilibrium with B, and I come along and I shove in a whole bunch of extra A. If I put extra A in there, it won't be at equilibrium anymore. But if the reaction shifts itself to create more product, in other words, shifting to the right to make more product, you're going to end up with yourself back at equilibrium. So if you increase the concentration of either a reactant or product, the reaction will actually shift to consume the added reactant. Otherwise, this part here of your ratio would increase and your K would change. A very important part about adding a reactant or a product is that K stays the same. It will go back to the same K value that it had before. Okay, so if you add a reactant or a product, the reaction is going to consume the added substance. Okay, it will always consume. So let's say instead of this scenario, we increase how much B we have. Now we have too much B. If you have too much of something, then you need to react it away, and it will shift to the left to produce more A. So if you have added reactant or product, whatever side you add it to, the reaction will shift to the other side. Shift means just form the other side. So instead of being at equilibrium, it's going to actually be reacting in one direction until it gets back to that same K value that it had before. So that is for adding a reactant or a product. Now, removing a reactant or product is the exact same idea. If you remove a reactant or product, it's gonna want to replace the lost substance. Okay, so let's say we have, again, a real simple idea of A is in equilibrium with B, and let's say we take away some A. If we take away A, the issue is we don't have enough A. So what does it need to do? It needs to make more A. So it's going to take B and make it turn into A. So if you were removing A, then you would have to get B to convert into A. In other words, shift in the reverse direction or to the left or make more reactant, whatever way you want to say it. The opposite is also true. So if we have A is in equilibrium with B and we decrease how much B we have, then this reaction is going to shift to the right to make more. So if you add extra reactant or product, like here, it's going to consume it. It's got to get rid of it by using it up. If you remove it, it's got to replace it. Okay, and it's very logical. I mean, that to me is very common sense related. You know, if you use up all the money in your bank account, then you are going to do something to replace it. So it's a very logical, common sense type concept. All right, so the next stress that we can do would be changing the volume of your container that your gas is in, and thus changing pressure. Just a quick reminder, if you increase volume, then pressure goes down, and if you decrease volume, pressure goes up, if you remember from Boyle's law in our gas law problems. So what we're going to do on these ones is, again, think of the stress in the exact same way we did with the adding of reactants or products. If we have a system that's in equilibrium and we change its volume, say we increase its volume, which decreases its pressure, now there's too little pressure for this reaction to be at equilibrium. Remember our K values, squeeze this in here, our Kp is our pressures of our products over our pressures of our reactants. So if we change the pressure, it's going to screw up the equilibrium, and the system is going to try to get back to equilibrium. So if you have, we'll look at the first bullet here, if you've increased the pressure on the system that was at equilibrium and you've messed the whole thing up, what the system wants to do is to reduce it back down. So if you have too much pressure, it wants to bring the pressure back down. And so what it's going to do is reduce how many actual molecules are in the container. That's the only way it has control over the pressure, would be to reduce the number of molecules that it has in its container. So that's how we're going to deal with the whole pressure thing. Let me get myself some space here. So let's say we had this reaction, and all of these are gaseous, by the way, in this example. So let's say we have 2A plus B equals 2C. So that's our reaction. So if this reaction was at equilibrium and I was to come along and increase the pressure, what the system wants to do is to get the pressure back down. So it wants to bring P back down. That's what it wants to do. So what it needs to do is it needs to shift to make fewer moles, make fewer particles. Let's say particles. And we can see relative numbers of particles in the coefficients. If you look on this side of the reaction, we have 3 moles of gas, and on this side we have 2 moles. So if this system wants to bring the pressure back down, it needs to shift to whichever side has fewer particles, because fewer particles are going to exert less pressure. So this reaction would shift to the right and make more C in order to bring down that pressure. Now, if you were asked the same question, but instead told that the pressure increased, oh, I'm sorry, we just did pressure increase. Let's say you were told that the pressure decreased, so the pressure went down. Now what you need to do is bring the pressure back up. And the way that you do that is by going to the side with more moles. Okay? So if the pressure is too low and we need to bring the pressure back up, then we're going to shift to the side with more moles. Okay? And you can see that again back up here, and in your notes we said that if the pressure was increased, it would want to decrease it, okay, which was here. So pressure was increased, means it wants to bring it back down, it shifts to the side with fewer moles. If the pressure is decreased, which is again done usually through a change in volume, then that means that the system wants to shift to bring that pressure back up, and the way it does that is to go to the side with more gas particles, shift to that side. So let's take a look at an example problem and take a look. I don't know why there's writing on here, but we'll go with it. So this problem gives us this equation right here, and then it says if we reduce the volume of the container that the system is in, what happens to the pressure? So if you take this system and you reduce the volume, so volume goes down, then that means pressure is going to increase. Okay, that means pressure is going to increase. That you need to deduce on your own because, again, that's just Boyle's law. Now with that pressure increase, we have to figure out which way this reaction is going to shift. So the issue is the pressure is too high. So what we need to do is to bring it back down. So to bring it down, we have to shift to the side with fewer moles. Okay, so we go back up here. On this side, I have 1 mole. On this side, I have 2. So to shift to the side with fewer moles would be to shift to the left. Okay. So take a look at that again. You're shifting to the side with fewer moles. We want to shift to the left. Okay, let's take a look at the next problem. Man, why do I have writing on here? So unprofessional. There we go. Okay, so let's take a look at this one. Now this one, notice, all they tell you about is the volume. You have to immediately realize when they tell you volume is decreased, that really what they're saying is that pressure increased. You have to do that yourself. And then they want to know which direction this is going to go to re-achieve equilibrium. So again, notice everything is gases. On this side, I have a total of 4 moles of gas. On this side, just 2. So if the pressure is too high, we need to bring it back down. So to bring it down, we want fewer moles. So we are going to shift to the side with fewer moles, which in this case is to the right. To make fewer particles, this is what your explanation would look like. Go to the right to make fewer particles, thus decreasing pressure. So again, we're looking at number of moles on both sides. If you flip your paper over to the back side, oh my goodness, don't cheat, don't cheat, don't look. There we go. If you flip your paper over to the back side, this is a special situation that I want you to see. So this one says, again, the volume is decreased. So if volume is decreased, they're telling you pressure was increased. And they say, what direction will the reaction proceed to re-achieve equilibrium? So you know the pressure is too high. So you know that it's going to want to come back down. So you know it's going to shift to the side with fewer moles. And of course, the opposite is true as well. But when you go up here to the top and look at your equation, in terms of gas, you have 2 moles of gas here and 2 moles of gas on the product side. So there's the same number of moles on both sides. If there are the same number of moles on both sides of gas, then that means that pressure didn't change the equilibrium in the Thank you. I'm assuming you said bless me. So if it has the same number of moles on both sides, that means that that reaction was not affected by this change in pressure. The only types of reactions that pressure will change with these gases is ones that have different numbers of moles on both sides. So your answer to this equation would be that equilibrium was not disturbed. And I would write due to moles of particles remaining the same on both sides. Okay, so that is change in concentration, either adding or removing reactants or products, and change in pressure. Now, both of these ones, we remain the same in terms of our value of K. I'm going to go back, if you would go back in your notes to where we had this changing volume and pressure, and make yourself a note here that K stays the same too. Both of these, what they are doing is re-establishing the same equilibrium they had before. So if their Kc, say, was 51, it got messed up when you added or removed reactants or products, but it's going to go back to that same ratio. Now, the reactant and product amounts are going to be different now, but the ratio is going to be the same. Just like if I said 4/2 is the same thing as 2/1. They both equal 2. So the ratio ends up staying exactly the same. That's for changes in pressure and changes in concentration. Temperature has its own special situation that we are going to have to deal with. temperature is going to get into a whole new realm of what actually is going to end up happening, and it's actually going to change the value of K altogether. So let's take a look at temperature. Okay, so there it is, great big slide. So it is going to actually change K. So you're going to be at equilibrium, you're going to change the temperature, K is going to get screwed up, and it's going to go back to equilibrium, but it goes back to a new equilibrium. So maybe your K was 51, now it's going to be something completely different. But what we can do is conceptually figure out whether or not our reaction is at equilibrium or not. Now, we can conceptually figure out whether or not our K value will go up or down. We know it's going to go back to equilibrium. Now, in class tomorrow, I'm going to go over this temperature portion. But the one thing I want you to be prepared before you come to class tomorrow to hear that discussion is what you have here in front of you. We've talked about endothermic reactions before, having a positive delta H, and exothermic reactions having a negative delta H. You already know that. You already know that endothermic means that it's absorbing energy. Exothermic means it's releasing energy. But you probably never looked at it in terms of how I have these reactions set up. You notice here on the reactant side of the endothermic one, we said endothermic means absorbs energy. Notice that heat is a reactant in an endothermic reaction. Okay, because absorbing energy means heat needs to be reacted with the reactants. Exothermic means that heat is produced. So you see heat as a product. Again, we don't normally write heat in, but for Le Chatelier's principal problems, we are going to need to include the word heat on the appropriate side. So what I want you to be prepared for when you get to class tomorrow is that endothermic means reactant side heat. Exothermic means product side heat. And that's going to really help you with what we're going to do, because whether or not K goes up or down with a temperature change is dependent on whether or not the reaction is endothermic or exothermic. Okay, so we will cover that in class tomorrow. Now, I gave you some problems to work on for tonight. Please make sure you do those. If this video gave you any issue at all, if there's anything you're not understanding, go back and rewatch it. I am going to very quickly cover this again at the beginning of class tomorrow and then get into the temperature change part. Okay, thank you very much for watching. See you tomorrow.